In this lecture, we will study the motion of charged particle in uniform and non-homogeneous magnetic field. First of all, we will discuss the motion of charged particle in uniform magnetic field. As we know that whenever a charged particle enters into a magnetic field B, the charged particle is acted upon by force, that is Lorentz force, which is given by QBB sin theta. Its magnitude is QBB sin theta. So we will discuss three different cases. First case is when the particle enters parallel to the field direction, that is theta is 0. In that case, the Lorentz force will be 0. Therefore, the velocity of particle will remain constant. So the particle will be undeflected. The second case is when the particle enters in the magnetic field in a direction perpendicular to the field. In that case, the Lorentz force is given by QBB because sin theta is 1, and this force is normal to both velocity and magnetic field. Here, the Lorentz force will provide the necessary centripetal force for circular path, and the charged particle will traverse a circular path. And just equating the Lorentz force with the centripetal force, we will get the radius of the path, circular path, that is mv upon qb. This radius is also known as Larmor's radius. And we can have the expression of angular frequency, that is omega is equal to speed upon r, and that is equal to qb upon m, and the frequency will be given by omega upon 2 pi, that is qb upon 2 pi m. This is important to note that this frequency, which is also known as cyclotron frequency, is independent of the radius of the orbit. It's independent of the radius of the circular path. It depends only on the magnetic field and the charge and the mass of the charged particle. Now, the case third, when the charged particle enters the field at certain angle to the field direction, in this case we can resolve the velocity component into two parts. The first is the velocity component v parallel, that is parallel to the direction of field, and another component of velocity is v perpendicular, that is normal to the direction of the field. V parallel will not contribute to the force. Therefore, the path of the particle due to V parallel will be a straight line, whereas the V perpendicular component will provide the necessary centripetal force for circular motion, and the radius of the circular path is given by this relationship. Now the resultant path will be the superposition of the straight line and circular path, and the trajectory of the charged particle will be of a helix or a spiral. In other words, the particle gyrates about the magnetic field. We can also say that the charged particle is locked to the magnetic field lines.